Good afternoon, everyone, and welcome for this wonderful webinar on astronomy, space, images, the JWST. I'm so excited to have Dr. Laura Parker, who is a professor and university scholar in the Department of Physics and Astronomy. I actually know Dr. Parker quite well because I took her Big Questions, which is 2B03, an astronomy course that sort of tackles all of the big concepts in astronomy. And it's for lay people like myself with a humanities background and not needing any of the math or physics. So I loved it. So Dr. Parker is an observational astronomer, and her research focuses on observational astrophysics, and her main interests sort of lie in galaxies and dark matter, all of which I learned in her wonderful course. So I'm so happy that she agreed. We put this webinar together very quickly because as those gorgeous images came out last week, we thought, oh, we need to do a talk on this. So we reached out to Dr. Parker, and she very kindly filled our request to do this talk. So over to you, Dr. Parker. Thank you for joining us.
Thanks so much. I'm really happy to be here. And this is indeed particularly timely. So the first results from the JWST just came out last week. And this has been the hot topic of discussions in the hallway around here. So I'm really happy to be able to share with you some of these exciting new results. And I'm going to focus on the 5 images or the 5 data sets that were released last week. But before we get to that, I thought I should give a little bit of context on what JWST is, what makes it so special, and at the same time to differentiate it a little bit from the Hubble Space Telescope, which is a telescope you may have heard about before. So here on the front page is an artist's impression of what JWST might look like out where it's located about 1.5 million kilometers away from us. It is this beautiful gold telescope. So the big gold hexagons you see, that's the main part of the telescope. That's what collects all the light. And it turns out that this is an infrared telescope, and gold reflects infrared light really, really well. And then you can see underneath the telescope this huge construction. And this is the sun shield. So this is what protects the telescope and all of the instruments from solar radiation. And just to give you a context for size, that big construction underneath the telescope is about the size of a tennis court. Okay, so let's talk a little bit about where JWST is. So it launched back actually on Christmas Day in 2021. And then it traveled this pretty large distance, over 1 million kilometers, out to this point in this diagram, which is labeled L2. So in the language of physics and mechanics, this is called the Lagrange point 2. So what is special about this location is that when you consider the mutual gravity of the sun, the earth, and the moon system, there are a few locations which are incredibly stable. And what that means is if you put something there, it pretty much stays there. You don't need to continually burn fuel to keep it there. And so JWST has been inserted into this location close to L2, which is one of these stable places. And it's a special one because it is orbits with us around the sun, which is really nice. So it takes us a year to go around the sun, and JWST just comes with us. So it's always in the same orbit as we are, a 1-year orbit. It's easy to communicate. We always see this location, so it's easy to send the data back down to Earth. And it's also from this location very easy for JWST to turn its back on the sun and keep its all of its equipment nicely shielded the whole time. So that's where JWST is. It's out there over 1 million kilometers away, collecting data right now and relaying it back to Earth. And just to highlight, this is one of the areas where JWST is quite different than the Hubble Space Telescope. So Hubble is in a low Earth orbit. It is orbiting directly around the Earth. JWST orbits around the sun. And the fact that Hubble is in orbit around the Earth means you could send astronauts to fix it. And you may recall there were a couple of NASA shuttle missions to upgrade instruments and fix some technical glitches on the Hubble Space Telescope. We're not going to visit JWST, so everything had to work. And I'm very happy to tell you everything worked. So the telescope was launched incredibly successfully, and all of the pieces along the way that brought us to the images I'm going to show you today, all of those steps worked at least as well, if not better, than anticipated. Another really big difference between JWST and the Hubble Space Telescope is the size of the mirror. And in astronomy, the size of the mirror is critical. So bigger telescopes collect more light. Collecting more light allows you to see fainter objects. And so with JWST, we'll be able to see incredibly faint objects that have escaped every other telescope so far. And in addition to being bigger means you can see fainter, it also means that you can see things at extremely high resolution. So it turns out that how small a scale of things you can resolve, so how fine a detail you can see, depends on how big your telescope is. So JWST is 6.5 meters across. Hubble, by comparison, is 2.4 meters, so just a little bit bigger than a person. So JWST is a lot bigger, which is great. It did mean it was challenging to launch. So it's 6.5 meters across. Our largest launch vehicles don't have that much space. And so JWST had to launch all folded up, and then it had to get to space and start unfolding itself and putting out that giant sun shield that's the size of a tennis court. All of that had to be very compact for launch, and all of it had to then unfold perfectly. And it did, and it's all working. Another critical piece before we start talking about some of the cool science you can do to note, which is a difference between JWST and the Hubble Space Telescope, is the kind of light that it observes. So when we think about light in our everyday lives, we usually think about the rainbow, which we call visible light or optical light. And the Hubble Space Telescope was optimized to look at that kind of light. So everything from purple to red. But if you are more blue than purple, that's the ultraviolet. We don't see it with our eye, but it's still light. If you're more red than the reddest you see with your eye, and we call that infrared, it's still light. And so in astronomy, we want to study objects at every wavelength, going from the highest energy, which we call gamma rays and X-rays, all the way down to the longest wavelengths through the infrared out into the radio. And the Hubble Space Telescope, as I mentioned, really focused on the visible part of the spectrum. James Webb focuses on the infrared. And so some people ask, is James Webb a follow-up or is it Hubble take two? And in some sense, it is that it's the next really big all-purpose satellite telescope in space, but it's quite different. It has a focus on different kinds of science questions because it's looking at infrared light, and infrared light tells us different things. And so the last thing I want to do before I start sharing the beautiful images from the JWST is I want to tell you why infrared is so special. So the things you can do using an infrared telescope that you can't do with a visible telescope like the Hubble Space Telescope. And the first one of those is the ability to see through dust. So in the universe, many of the most exciting places near black holes, in the densest parts of galaxies, which is where stars and planets are being born, that material is a lot of gas and a lot of dust. And it turns out dust has this remarkable ability to absorb and scatter light. And I mean, you can even think about this if you've ever had a particularly dusty room and the sunbeams come in the window on that sunny day and you have a dusty room, you see the light scattering off all the dust particles. And it's the same as that in space, except that we can have so much dust that it completely blocks light from anything within it or beyond it. And so on the left-hand panel here, you can see a region of space which is within our own galaxy called the Milky Way. So somewhere within the Milky Way, this is a region of dense gas and dust. And we care about it because within that is where stars are being born. And with stars, you also form planets. So deep within this cloud of gas and dust is where stars and planets are being born, but we can't see it with visible light. On the right-hand side is a near infrared view. So when I say near infrared, I mean just redder than what you can see. Mid infrared is much redder than you can see. And that will be important in a minute when we look at some of the JWST images. So left is visible or optical light, right is infrared. And I hope you can see right away that you see way more stars. So if you just counted the stars in the picture on the left versus the right, you see way more stars. You are seeing through an awful lot of the dust if you can look at this part of the universe with an infrared eye. And this is pre-JWST. So this is going to get much, much better. So reason number one to use infrared is to see through the dust. Reason number two, which is the one that gets me the most excited, it relates to the research that I do, is to be able to study the most distant galaxies in the universe. And it turns out that there's this really remarkable property that light from distant objects, as it traverses the universe, the wavelength of that light actually gets stretched out. So what that means is if something emits blue light, as that light travels through the universe towards us, the blue wavelength of light gets stretched and it becomes redder and redder and redder. So if I study an object that is 5 billion light years away, the light will have a certain amount of redshift. So maybe if it was emitted as blue light, it would look red to me in my telescope. But once I start to look at objects even further away, say 10 billion light years away, the light that was originally visible, blue, green, or red light, has now been redshifted so much that the light is actually only observable in the infrared. So the galaxy emits light in blue or red light, and we see it in the infrared if that galaxy is far enough away. And why this is so powerful is that it's going to allow us to see the most distant galaxies whose light is emitted at bluer wavelengths, but we see it in the infrared. And right now we don't have until JWST, we didn't have a powerful big infrared telescope in space. So the Hubble Space Telescope could only see galaxies so far out, then it would reach a limit. We want to see beyond that, and that's what we can do with JWST. So there's an amazing richness here in looking at the most distant galaxies. And I should note, really important concept is that as you look out to ever more distant objects, you're actually looking back in time. And that's because light doesn't travel instantaneously. It takes time for light to reach us. So if I look out the window right now and I see sunlight, that light was emitted 8 minutes ago by the sun, and I'm seeing it now. The galaxies we're looking at, that light was emitted billions of years ago. So we're seeing the universe as it looked billions of years ago. So we're looking back in time. And that is one of the big questions in modern astrophysics is what was the beginning of the universe? What did the first objects look like? And by having an infrared telescope, we hope to be able to learn a lot more. Third reason for studying things in the infrared is there's some really important, interesting information in this part of the electromagnetic spectrum. So electromagnetic spectrum is everything from gamma rays to radio. Turns out in the infrared, there's some really important information, including signatures about atmospheres. So what I'm showing you here is something called a spectrum. So if you take light, imagine you take, again, sunlight, and you put it through a prism, then you see the whole rainbow of all the sunlight. We do this in astronomy. We take light from objects and we disperse it so you can see exactly how much light there is at every single wavelength. But if that light is not coming from the sun, but is coming from, let's say, a cloud of hydrogen gas, you will only get light at very certain wavelengths that correspond to hydrogen. Or if that light is glowing with oxygen, then you would see lines corresponding to oxygen. Every element and every molecule has a unique signature. And so this is a spectrum of the atmosphere of the Earth. And it's how much light you get as a function of wavelength. That's what a spectrum is. And what you can see here are a bunch of lines, and they're labeled with different molecules that you find in the Earth's atmosphere. So this is what we want to do, not for the Earth. We know what the Earth looks like. We want to do this for extrasolar planets. So what do I mean by that? I mean the thousands of planets we found in the last 20 years that are orbiting around other stars that are not the sun. And so far we have found many of them, but mostly we just have basic properties like how big are they, what's their mass. We want to now understand them in much more detail. Could those planets be places that have life? What do their atmospheres look like? And if you want to do that, you need to look in the infrared. So most of these interesting features in the Earth's atmosphere, you see them in the infrared. And the fourth and final reason to look in the infrared is that you can't do any of that cool science I just told you, the planet atmospheres, the most distant objects, the looking through the dust. You cannot do that from telescopes on Earth. So this cartoon is a little confusing perhaps, but what's shown is light from space, how much of it reaches the Earth. And if you have, like on the left, you have this black line is quite high up, that means that the light does not make it to the Earth's surface. If it's blue all the way down to the bottom, that means that light makes it to the Earth's surface. And on the left, you have high energy light like gamma rays and X-rays. And on the right, you have lower energy, redder light like infrared and radio. And what an important thing to note here is that visible light, makes it through to sea level? Of course it does. If you go out tonight and look at the night sky, you can see stars. Your eyes are seeing stuff in space. That means visible light makes it through our atmosphere. Infrared light, the middle part of this diagram, most of the infrared light is blocked by our atmosphere. So our atmosphere is filled with all kinds of elements and molecules, and they interact with light from space, and they love infrared photons. So most of the infrared light gets absorbed by our atmosphere. So you can't do all of that cool science. You cannot do it from a telescope on Earth. You have to go to space. Excuse me. Okay, so now to the main point of today's session. Let's talk about these first images that were released last week. Here's the first one. So this one was released one night before the others, and it was actually released by President Biden. And this shows the first deep field by JWST. And a deep field is basically take a patch of sky that doesn't have any obvious nearby structure. So there's no like big nearby galaxy in the image. Open the shutter on your camera for a really, really long time. In this case, it's a 12-hour exposure. Some of the deep fields observed by the Hubble Space Telescope were observed for 20 days. So this is a 12-hour exposure. And the richness in this image just overwhelms. There's so much going on, but let me try to explain a few of the things that you're seeing. So first thing that might pop out to you are these big spiky objects. Those are actually not the interesting part in the image. Those are stars, not galaxies. Those are individual stars in our own galaxy, the Milky Way. So anytime you want to take a picture of the distant universe, you have to look through our galaxy to see that. And when you do that, you get a few foreground stars in the image. So that's the spiky things. Every other point of light you see there, basically, is a galaxy. So there's thousands of galaxies in this one image. And the other thing I hope you can see is that some of those galaxies look kind of weird. They're very distorted. So you have these huge arcs, very distorted galaxies. That's not what the galaxies intrinsically truly look like. Those galaxies have undergone a process called gravitational lensing. And I could give you a whole talk on just lensing and how powerful it is, but just quickly to explain how it works, this is something that was predicted by Einstein with his theory of general relativity. But the idea is we're here on Earth or near Earth with JWST looking at the night sky, and we have some background objects. So in this case, it's a galaxy on the left-hand side. And if we were just looking at that galaxy and there was nothing between us and it would look like it intrinsically is. However, if there's something really massive along the line of sight between us and that background object, the light from the background object, according to Einstein, actually gets bent. And so that object it can look magnified. You get multiple rays of light. It can look brighter, and it can also look very distorted. And so that's what you're seeing here. If you can note in the middle, there's a bunch of kind of whitish, slightly, maybe lightly, a little bit orange, fuzzy blobs. Those are all galaxies that live at one distance from us. They live in something called a galaxy cluster. So there's a galaxy cluster in this image. It's about 4.5 billion light years away. So that the solar system was just being formed at the time that that light was emitted, which is mind-blowing. So you've got a cluster, and then you've got background galaxies behind it. And those background galaxies are what you're seeing distorted here. And I think it's nice to actually zoom in, and look at an individual one. I'm going to come back to this in a sec. So here's an individual galaxy that is highly distorted by this lensing effect. So this huge orange fuzzy thing is probably a pretty normal galaxy. And to our eye, it looks so distorted because of this gravitational lensing. So I think they chose a very good field for their first deep sky image. And it's not surprising they chose it because this was a field that was also observed by the Hubble Space Telescope. So the Hubble view is on the left. The galaxies in the cluster look very orange. The JWST image is on the right. And I hope you can see right away in the JWST image, there's actually more galaxies. So these are not perfectly to scale, but I think you can probably match like the bright star in the left to the bright star in the right. There are more galaxies on the right because this is a deep field with lots of really distant galaxies in it that really become much brighter in the infrared. So the big infrared telescope of JWST is incredibly rich for studying these distant galaxies. The second thing I want to show you is an important Canadian contribution. So this is not an image, this is now a spectrum. And I showed you an example spectrum from the Earth's atmosphere. Now here's one for an extrasolar planet. Amazing. So you're seeing the chemistry in the atmosphere of an atmosphere around a planet, which is orbiting some other star far away, not the sun. Now, this is a pretty strange planet. It's called WASP 96b. It's strange because it looks like nothing in our solar system. This planet is about the same size as Jupiter, but it orbits its parent star on an orbit that is smaller than Mercury's. So if you remember, Mercury is the closest planet to the sun in our solar system. This planet is much closer than Mercury. So what that means is it's whipping around its parent star every few days. So we don't have a giant Jupiter-sized planet doing that in our solar system. So this is not like us. However, this is its atmosphere. It has water in it. So what you can see are these features, and they're labeled H2O. So we see that there's water in this atmosphere. And on top of that, the best fit model, which also fits the structure of all of those lines in the spectrum, tells us that the water is not everywhere equal. It's patchy. And so JWST's first characterization of an extrasolar planet finds clouds on a giant planet orbiting its star. This is patchy, hazy, cloudy water vapor in the atmosphere of an extrasolar planet with a Canadian-built instrument. It's amazing. Third image that was released was of an object called a Planetary Nebulae, and in particular, this is the Southern Ring Nebula. And there's two images of it here. So the one on the left was taken with one camera on JWST, and that looks at light just redder than your eye can see, near infrared. And on the right is further out into the infrared, called the mid-infrared. First of all, stunningly beautiful. I should note that a planetary nebula is an old-fashioned name in astronomy that's kind of a misnomer. This has nothing to do with planets. A planetary nebula is what's left over when a star like our sun dies. So there are kind of two pathways for stars at the end of their life. Stars are big nuclear engines fusing energy in their cores, but eventually they run out of fuel. And if you're a really big star, you blow up as a supernova. That's what happens. If you're a lower mass star, like our sun is, then at the end of your life, you run out of fuel and you become a degenerate little object called a white dwarf. And when you do that, you shed your outer layers. And I'm happy that this is what happens because you get these spectacular views. So this is those outer layers being sloughed off as the star evolves. Why many people who study this field were incredibly excited was actually from the image on the right, the mid-infrared view. And why they were so excited is because hopefully you can see there are two objects in the middle. A white dwarf is pretty faint, and we don't tend to see them in the middle of planetary nebulae. A white dwarf is what's left over. So on the left, you see this star in the middle. That star is not what's causing the planetary nebulae. What's causing it is a white dwarf that had never been seen before. And in the right, in the infrared, because you can see through the dust, you see it. So for the first time, the white dwarf in this system was directly observed. And in fact, I looked it up and there was a paper way back in 1968 predicting this system had a binary, which means two stars in orbit around each other, a white dwarf and a regular star. And up until last week, only the regular star had been seen. This is also an image where it totally pays to zoom in. So, oh, sorry, there's the white dwarf. Let's zoom in. Before we do that, again, Hubble did see this. The JWST image shows much more structure, high resolution, much more detail, and you start to see background galaxies as well, because JWST is just so sensitive to those distant galaxies. So if I zoom in here on this little piece, if you're interested in planetary nebulae, this is such a rich data set. There's so much going on in that gas and dust that you can study and study the physics of what happens in stars at the end of their life. If you're someone like me who studies galaxies, I just find it amazing that these background galaxies are poking out through the view of the planetary nebulae. And this is what it's been looking like in every JWST image I've seen so far. There's just background galaxies everywhere. It's amazing. Okay, so number 4, the one I was anticipating the most. I was really waiting for this because I knew they were targeting this object. This is called Stefan's Quintet. It is a system of 5 galaxies that on the sky are really close together. It turns out that in space, 4 of them are at exactly the same distance and they're interacting. one of them is just projected on that part of the sky, but is actually not that close by. So the one on the left is a close by object. And then on the right, you have galaxy 1 on top, galaxy 2 and 3 interacting here, and the final galaxy down on the bottom. So the 4 on the right-hand side of the image are all interacting with each other. And this image blew me away as someone who studies galaxy evolution, because the merger of these galaxies, their interactions, are causing all of this stuff to spew out into space, which we can see because JWST is so sensitive. Also, this really bright red region between these galaxies, there's actually star formation in this gas that's causing it to glow. And usually we only study star formation within galaxies. This isn't stuff that's been stripped out of galaxies. So that's incredibly exciting. So this is a combination of near infrared and mid infrared together. But if we again focus on, well, before I do that, just look at the background. You can see background galaxies everywhere here. Every image for free, you get all these background galaxies. If I switch to the mid infrared view though, and only look at the very red light, this is really exciting too. So this is where we've lost the galaxy off the bottom, but you've got the foreground galaxy here, and then a galaxy on top, and then the 2 merging ones at the bottom. And when this image was shown in the room, I was sitting in with a bunch of astronomers last week. We all went, oh, we were all really excited. And the reason is this pointy object in the middle. So if you remember back when we looked at the deep field image, I said stars are the big pointy things that are in the foreground. Really what I should have said is any object which is a point source for the telescope, point source versus an extended source. So something that all the light's coming from one point compared to an extended source. Anything that's a point source creates that spiky pattern in any space telescope image. And the exact kind of spiky pattern depends on properties of your telescope. What does your mirror look like? What does the structure of the telescope look like? So Hubble's looks different than JWST's, but a point source is something that's so small you can't resolve it, even with the amazing resolving power of your telescope. That was a long-winded explanation. Why am I so excited by this point? It's a point in the middle of a galaxy. It's not a star. It's not there in the near infrared view. This is a supermassive black hole that is feeding on gas in the middle of this galaxy. So black holes, compared to the size of a galaxy, black holes are tiny, so they're a point source. And of course, a black hole, by definition, you don't see it. However, if there's gas and dust near a black hole that's falling into the black hole, it gets heated up and it glows. And if it's dusty, it glows a lot in the infrared. But it's so on such a small physical scale, it's going to look like a point source, and it's going to create that spiky pattern. And you can see it in this image. So you are seeing an actively feeding black hole in this gorgeous image. And then the final image I wanted to show, which is the final image of the 5 images that were released, is the Karina Nebula. So this is that science question of looking through the dust to see what's happening with star formation within our galaxy or nearby galaxies. This is within the Milky Way. This is an area rich in gas and dust that is right now forming tons of stars. There's actually a whole bunch of stars in the blue part on top here that have recently formed that are spewing out tons of radiation, ultraviolet photons, and they are irradiating this gas and dust and pushing against it. And that's what gives it this pretty sharp edge. There's also light leaking out from star formation out of the gas and dust above. So many stars that you can see through the dust here that you could not see in the Hubble Space Telescope image. So for people who study star formation, this was the image that got them just incredibly excited. So this was the first 5 images, but we've already got a whole bunch of data since this. So this was NASA's big press release with all the nice images and everything. But data is being taken every moment and being downloaded. And I have colleagues all over the world working on it, including one of my most recent PhD student who finished last year. He has a postdoc working on JWST data. And so he sent me some preliminary stuff a couple days ago. Incredibly excited. So this is just the beginning. 4 main science goals for JWST: to study the early universe, the most distant galaxies, to study galaxy evolution over time, for example, using Stefan's Quintet and other systems of interacting galaxies, to study the birth of stars like the Karina Nebula, the death of stars like that Planetary Nebula we saw. And then another, of course, really exciting science topic is characterizing extrasolar planets and trying to understand other worlds. So I will stop there, and I'm really happy to take any questions that people have.
Hi, Laura. All right, thank you. That was a reminder of the 2B03. Lots of content I remembered from that from 2 years ago. We have so many questions. It's blowing up in here. The first question that I wanted to ask, it actually came in the pre-submitted questions. So thank you everyone who pre-submitted the questions. So probably you could tell many of those questions Laura tried to answer in the presentation, but we'll get to the other ones. It is 1 o'clock now, and we said this would be a short talk. So if you need to leave, feel free to leave now. When we get into Q&A, we can stay on for 30 minutes, 35 minutes or so to answer questions. And if you are unable to remain on, then you will get the Q&A in the recording that we will send out to everyone probably at the end of the week once we're able to upload it and closed caption it. So the question I have for you that came in, and you sort of alluded to it a bit when you were talking about, what was it, WASP 96B, the Canadian contribution. So the question was, describe the Canadian contribution to JWST, the equipment built by whom, and what science depends upon the Canadian equipment?
Fantastic. So in anticipation of this, I have a couple of extra things, but first to note that unlike the Hubble Space Telescope, which we have access to because the way that publicly funded telescopes work in many countries, including the United States, is anyone can apply for time. So you can get science time on Hubble Space Telescope, but we didn't build any of the instruments. We were not a key contributor. That's very different with JWST. Canada built 2 major contributions. One is called the Fine Guidance Sensor, or the FGS, and the other is NIRISS, the spectrograph, which took that amazing spectrum of the extrasolar planet where we saw the cloudy water. And FGS is needed for all of JWST. So if you want JWST to point to the right part of the sky accurately to get you your target, there's a Canadian contribution that allows that to happen. So that is a critical piece of infrastructure for everything that is done. And then the near infrared spectrograph, NIRISS, is one of the 4 key science instruments. And it has 2 modes. One allows you to take a spectrum of one specific object, and that's what that extrasolar planet was. And then there's another mode that allows you to get kind of a coarse spectrum for everything in your field of view. And so what that means in terms of science, which was another part of this question, is the key science for the Canadian contribution is these extrasolar planet atmospheres. So that's the single target. Or my kind of science, which is studying galaxies. If you have a bunch of galaxies in the field and you want a spectrum for a whole bunch of them, then this other mode that allows you to get a coarse spectrum for every pixel in your whole image, then that's something that NIRISS can do. And in terms of who led this contribution, so the contracts went through the Canadian Space Agency. The main industrial partner was Honeywell, but at the beginning of the project, it was ComDev. So ComDev got bought by Honeywell because this project started when I was an undergraduate, so it's been decades. So some of these companies have changed hands. So it's Honeywell, and then the academic PI is René Doyon at University of Montreal. And so those are really the leads on the project.
So important Canadian contribution then.
Major Canadian contribution. And that also means that in addition to the time that all of us as scientists can apply to target our favorite things, Canada got some guaranteed time for projects for science with NIRISS that before the rest of the world gets to use NIRISS, some Canadian astronomers get to. And also there was some special funding through the Canadian Space Agency for people to hire postdoctoral fellows to work on some of the science because we were such a major contributing partner. So it's NASA led, but Canada built one of the 4 instruments, which is remarkable.
Oh, that is remarkable. Exciting. Yay, yay, Canada. So going through, so Dolores has a question and she wanted to know, so NASA released the 5 images that you've talked about. She'd like to know, what are the next set of targets?
All over the map. So there's already been a whole bunch of things observed. So all of these science questions. I know of some very nearby big spiral galaxies that are already, the data is already available, where it's not just images, it's spectra of every region of those nearby spiral galaxies. I've seen some of that data, so I know that it exists. And I know that there's another one of the extrasolar planets that everybody was waiting on. There's a spectrum for that. It just turns out that with the JWST data, The star that the planet is very near, because the JWST data is so good, they understand also the star better, and the star is more complicated than they thought. So interpreting the planet data is just going to take a little bit longer. And that's why they didn't release that one. They released the WASP planet instead. So literally every single day, there are new data sets being downloaded. And if you're an investigator on one of those projects, then you get notified that your data is available. The rest of the world has to wait a little bit, and then we get to see all of it too. But I've downloaded the data for Stefan's Quintet, and I've been playing with it myself, doing some science on the images. So even astronomers just love to look at these images, but what we do, the analysis we do, is not with these multicolor images, it's with a slightly rawer data set.
Right, so the pretty pictures are for the public.
No, for us too. I mean, we love them. They're amazing. And it also makes you see things that makes you want to go and look more. But all of the images that I analyze are grayscale. So I treat a red image independently of a green image, independently of a blue image. Each one of those is a data set that I study. So I don't work directly on the color data, which is a representation, but is not what you use for science typically.
Okay, thank you. So going back at the very beginning of your presentation, you talked about JWST and the orbit. So a question came, where is Hubble's telescope ST? I had a couple questions about that.
Where is Hubble?
Yes.
So Hubble is, you'd have a hard time seeing it on this picture. It's between the Earth and the Moon on this graphic. So it's in a low Earth orbit. So it directly orbits around the Earth, much closer to the Earth than the Moon is. So it is a very different location than JWST, which does not orbit around the Earth. It orbits around the Sun, way further away. So the Hubble Space Telescope, you can measure it in a couple 100 kilometers per second, 100 kilometers away. JWST is 1.5 million kilometers away.
Big difference.
Big difference, yeah.
That's why the resolution and everything is so much better.
It's not exactly. So the resolution has to do with the size of your telescope and the wavelength of the light. But to do infrared astronomy, you're much better off going to this faraway site, far from the glow and the heat of the Earth. So it turns out that the Earth is pretty bright in the infrared, and everything glows with heat in the infrared. And so if you put your telescope too close to that, it wouldn't work very well, and you'd have to cool it a lot more. If you put it further away from any planets, then all the instruments are nice and cold, and they can detect infrared photons from space much more efficiently.
So the further out you go, then the better it is. Or at one point, does it not really matter? Like if you're a certain distance from the sun, it doesn't really matter then where.
Yeah, so the planets are bright in the infrared. So you don't want to be too close to planets, and the sun is bright. You don't want to be too close to the sun. But there's also a happy medium, because once you get too far away, then communication link gets hard. And so this is kind of a sweet spot. So this L2 location is very stable, so you don't have to waste much fuel to stay there. Once you park there, you're pretty much there. And you're still close enough that it's easy to send all the data back down to Earth efficiently.
Right, and speaking of orbit, we had talked briefly before everyone joined us about the damage that was done. So we did have a question from Raj. How has the recent impact with space rocks affected the telescope? I read somewhere that the damage was worse than anticipated, but they were able to correct the mirrors.
Yeah, so one thing about being in space is that it's kind of a hostile environment, and there are two main ways you can damage things in space. One is micrometeorites. So that is little tiny bits of dust and debris that are everywhere. It's the same thing that gives us shooting stars or meteors in the night sky. Most of those things are only microns in size, but they're moving really, really, really fast. So even a small mass moving at a high speed injects a lot of energy. It can do damage. And so it was in the news recently that a micrometeorite hit one of those pieces of the big mirror of JWST. And indeed, it did do some damage. And thankfully, it's one small part of one mirror, one segment out of a big telescope. So it's not affecting the overall image quality, but there's one segment of the mirror that is not working as well as the rest. And some of that damage is not really reparable. What was surprising about it was the size of the damage was the kind of event they thought would be very rare. And so the question is, were the estimates wrong and we can expect more of those kinds of events, or were we just really unlucky and in the first couple of months of JWST operating, it got hit with something that's really rare? Both of these are possible, but we don't have the statistics yet because it hasn't been in space long enough. But you can expect some more over the lifetime of JWST. You can expect some more micrometeorites. The other thing that damages things in space are something called cosmic rays. So these are high energy, often photons, could be protons as well, coming from energetic things out there in the universe like supernovae and black holes, ejecting stuff at high speeds. Those can damage more often not the mirror, but the pixels in your detectors. So for example, Hubble Space Telescope, one of the reasons why we updated the cameras, astronauts went and updated the cameras, was to put in new detectors that had no cosmic ray damage. Because once you fry a pixel, that pixel is dead. Other pixels still work. And there's millions of pixels in every image, but you can fry individual pixels with cosmic rays. So that means that no spacecraft taking images in space can operate forever. Even if it had fuel, even if everything else was fine, eventually the detectors will degrade because they're exposed to this harsh environment.
Nothing lasts forever. So bigger is better, and nothing lasts forever is what are two idioms that speak truth. So going back to infrared, Tyler has a question. Could you explain how these RGB images are formed from infrared wavelengths and how the red, green, blue equivalent to IR is chosen?
Great question. So in anticipation of something like this, I made a quick little image here. So this is RGB is how we typically make optical color images. It's how your eye does it. And in astronomy, we don't take a color picture. And even in your cell phone, when you're taking a color picture, it's actually software that's combining things. But we take images with filters that only let in light of a certain wavelength. So in this example here, this is a beautiful picture of a star forming region in the Milky Way. The red picture is on the left, the green picture is in the middle, which on this is labeled visual, and the blue picture is on the right. They're all grayscale. So you in software combine them, call one of them red, call one of them green, call one of them blue, add them together to make your color image. And if you're trying to highlight a certain feature, maybe you weight the red image more. So you want to really, show where the red features are in this image as an example. So the raw data, the top row of grayscale images, that's the truth. The bottom row, you get to assign what color do you assign to each of these filters. So this is an optical view, and it makes sense. Optically is easy because red light is red to our eye, green light is green, blue is blue. We can translate what we see in a telescope to what our eye would see. So the bottom color image in the bottom right is, if your eye was as big as the Hubble Space Telescope, that's what you would see if you looked at that part of the Milky Way. Now, once you move out of the optical, you can't do this anymore. I don't see infrared photons. I don't see ultraviolet photons. So I have to assign them some color in software to make a nice color image that you can see. And just as an example, here's one of my favorite galaxies in the universe. This is the Cartwheel Galaxy. And this particular version put together by people at NASA combined X-ray data and they assigned it purple. And infrared data, they assigned it red. And so the basic philosophy is to try to keep the order that you assign consistent with the wavelength of light. So X-rays are the highest energy light in this composite. So they get the purplest, the bluest of the blue. Infrared is the lowest energy, so it gets the reddest. And if I was only going to make an infrared image, let's say I wanted to make an infrared image, I would give the near infrared colors closer to the optical, I'd make them blue. And the very infrared colors, I would make them red. So there's some freedom in how you do it. You always know the truth with each individual image, but you get a little bit of creativity for what color you assign to make a beautiful final color image. And this is just a really fun thing that people get to do to make these public relations quality, beautiful color images. And there's a little bit of subjectivity and creativity in how you do it. Also, astronomers, we tend to be honest with, like, we have a coordinate system in our minds, north, south, east, west, and that's what we show. But maybe that image would look more interesting if you showed it like this, or if you flipped left and right. There's no reason not to, but so in these public releases, someone could, if they wanted to, rotate an image to make it look more visually interesting. Astronomers working on this data try to keep it in the normal coordinate system that we understand.
Oh, interesting. Okay, so lots and lots of questions. Do imaging of deep sky objects, this is from Edward. Edward does imaging of deep sky objects and uses narrowband filters. But people always ask me if those are the real colors, and I have to explain that I have added colors to the monochrome data, false colors, which is exactly what you're saying. So even minor astronomers do the same thing.
Yep. So amateur astronomers also do, anytime you do astrophotography, that's when you take pictures of space, you tend to take it with a filter, and that could be what we call a broad filter, like red, blue, green, or what Edward was mentioning was using a narrowband filter, which is a narrower range of wavelengths. Same principle applies. If you want to make a color image, you have to give it a color. So is it a false color image to some extent? Yes, always. But this RBG representation for visible is pretty close to what your eye would see. But even everyone's eye is different. We don't all have exactly the same sensitivity to red, blue, and green.
So here's a question. You showed the beautiful image that came up of the, the Karina Nebula. So someone asked if we could fit our solar system into that. Mm-hmm. Could you tell us the scale?
Oh, good question. So I don't know exactly the size of this, but it is on the order, which is what astronomers and physicists love to say, order of magnitude. This is a few hundred light years across. So the whole nebula would be a few hundred light years. And that is just way bigger than our solar system. So as I mentioned, the sun is 8 light minutes away from us. So the whole solar system for us is light hours. That's it. And this is 100 light years or a few hundred light years across for the Karina Nebula. So this is on the scale of many, 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 many well spaced out solar systems in terms of scale.
Sorry, lots of questions. So I think you answered. So John asked a question, will the JWST be able to do spectroscopy on the distant galaxies, and what would this tell us? So I think yes, because I think you talked about that.
I did, although I can even show you one. So this is something that came out after the original 5 data sets were released. So remember that deep field with the gravitational lensing that was so amazing? If you zoom in on one of the little tiny smudges that looks like nothing, the red little blob here on the left, JWST has such a big telescope and such amazing instruments that it can take a spectrum of something really faint like that. Taking a spectrum is harder than taking a picture because you take the light and you spread it out. So if you don't have enough photons, if the thing is too faint, you can't take a spectrum. So this little tiny fuzzy blob, you can't take a spectrum of this with any other telescope. JWST took a spectrum of it and found all of these lines. And why this is so exciting as somebody who works in this field is this object is 13.1 billion light years away. So we're looking back in time, 13.1 billion years. It's further than that away. 13.1 billion years. The universe is only 13.8 billion years old. So we are looking back to very early times. Any of the previous work that's tried to take spectra of objects like this, you might find one line, and then you have to try to guess, is that a hydrogen line or an oxygen line? Exactly what am I seeing? And in this one very quick spectrum taken of one object in this field by JWST, there's all these lines. So you can study the chemistry of a galaxy when the universe was only a few 100 million years old. So, yep, JWST can do spectroscopy of distant objects, and it's already doing it, and it's amazing. And very exciting for someone like yourself. Yeah. I can hear your enthusiasm. We all can hear your enthusiasm.
So someone asked, the black hole, that beautiful picture of the black hole absorbing, is that a quasar since it's actively feeding and emitting radiation?
That's a great question. So quasars, so let's just go over some nomenclature. Every big galaxy, from all the evidence we have, every big galaxy has a big black hole in the center. And we call those things supermassive black holes, or SMBH, because astronomers love acronyms. Some supermassive black holes are just passively sitting there and they're dark and you don't see them. You detect them by their gravity, but you can't see them. Some of these supermassive black holes are accreting material. So there's gas and stars and stuff falling into them. And then the material around them is hot and it glows and we can see them. And we call those active galactic nuclei. So they're in the center of galaxies and they're active. Then there's the extreme tail of active galactic nuclei. And those things are called quasars. Quasars are so bright that all you see is the point source. You don't even see the host galaxy. So you can't see the galaxy, you just see this bright point source of the quasar. Those were very common in the early universe, and we don't have any of them today in our nearby surroundings. This system is in our nearby surroundings. It's quite close to us, this collection of galaxies. And so that object is a very bright AGN, but does not qualify under the definition of quasar. It's just not quite bright enough, and you can see the galaxy. So it's almost a local quasar, but not quite.
So when you say it, everything's relative, obviously. When something is considered close in distance to us, what is not close in distance? Like how many?
So this would be, so for me, if you're within, if you're less than 1 billion light years away, then you're close. So, but this particular set of galaxies is tens of millions of light years away.
Oh, so it's very close.
Yeah, so these things are hard to, these numbers, I know they're huge and they're hard to wrap your brain around, but galaxies that are, this big in an image, they're not the little tiny background ones that are a few pixels, they're this big. You can basically tell by the size in the image. If it's very big, it's quite a nearby galaxy. So any of the JWST images that show one big galaxy or a couple of galaxies, those are going to be what I would call local. And then the ones like the deep fields where you have 1,000 galaxies in one image, those are distant galaxies.
Thank you for clarifying that. We have a few questions about specifically JWST. So who decides where it gets viewed in the universe, like where it gets positioned, I suppose, and how long will it stay up? How long will it remain in service?
Yeah, these are really good questions. So all of our observatories are competitive to get time on. So I can speak from the example of the Hubble Space Telescope, which operates in a similar way. So I've been on the time allocation committee, is what it's called, for the last 3 years for Hubble. So what happens is people all over the world have science ideas, and they have to, there's once a year where there's a big call that goes out for, okay, April 22nd, proposals are due, here are their parameters, here's how much time is available on different instruments. And then you write your science proposal using, being as strong as you can to make your case, because everybody wants to use the space observatories to do their science. And so what we call the oversubscription rate, which is how many things get asked for versus how many times things can actually get scheduled on the telescope, because there's only so many nights a year, it's about a 10-to-1 oversubscription. So if 10% of your proposals get accepted, you're doing on average what people get. So JWST works the same way. In advance, there's a call for proposals, people write down their best science ideas, and there's a science justification and a technical part. And the technical part is where you would say, I'm going to use this instrument in this mode, my images will take this long to acquire. So all the technical details, and both the science and the technical side get reviewed by experts, peer experts. They get ranked, and only the top few actually get scheduled. So it's incredibly competitive. And then the second part of the question was about the lifetime. When JWST was being designed and the plans for launch, everyone said 5-year lifetime. So that was like the minimum. Everything had to work for at least 5 years. And the main limiting factors, there's a few. One is some of the instruments have moving parts, and moving parts working at cryogenic temperatures do have a failure rate. And so at some point, some things will just stop moving. That's a problem. But the primary things were the amount of coolant, because you have to actively cool anything that works in the infrared. Even the telescope itself just kind of glows in the infrared, so you have to cool it. And the third thing is amount of fuel. So although JWST is sitting out there at Lagrange point 2, it's not exactly at L2. If it were exactly at L2, then the Earth would actually block the sunlight, which powers the solar panels. So it's on a little orbit around L2, which takes a little bit of fuel. But we're really, really lucky. The launch inserted JWST into its location using less fuel than most people predicted it would. So there's more fuel on board. And that turns out to be the primary limiting factor, is how much fuel it has. And so now the predicted lifetime, it went from 5 years to 10 years around launch. People were saying it looks like it will get 10 years. And now the prediction is 20 years. So
wow.
yeah, so JWST, if all goes well, should be operating for many, many years. Over that time, there'll be some degradation. Maybe one of the instruments might break, moving part might break, cosmic rays will damage some of the detectors a little bit. But in terms of continuing to be able to do science, we have way more than a decade, and that makes many people very excited.
Yes, obviously. Now, a question, when you talked about, the proposals and, there's limited time, but NASA releases information. So if you didn't need something, well, I shouldn't say need something specific, but you're always able to get information. It's just whether or not you can get specifically what you want.
Yeah, that's exactly right. So one of my favorite things about astronomy is actually that all of our data becomes publicly available. So that is definitely true for JWST and Hubble. And as a Canadian, it's true for all of our telescopes, because science in Canada is not done by private consortiums, or universities don't buy telescopes. The government gives us access to these things through the National Research Council. The string that comes attached to that is all of the data becomes publicly available. So in fact, the vast majority of the research we do in my research group is with archival data that other people propose to observe that field to do some science, but that data is sitting there, and then we're going to go and use it for some other purpose. And then sometimes we write telescope proposals for very specific things, but often we can do really cool science with what's in the archive. Like, look at this image on the screen, for example. Someone might have written a proposal to study the AGN in the center of that galaxy, and that's what they were interested in, and that's why the data were taken. But let's say you're really interested in the galaxy on the left, which is a little bit closer to us. It's a foreground object. Those blue blobs all over there, every one of those is actually a collection of these special molecules called PAHs, these big organic molecules. Maybe that's your science. So why would you go propose to view that galaxy when somebody else's observations just serendipitously got it for free? So it's a lovely thing about astronomy compared to, like, most of science is done in people's labs and you own the data and you publish stuff in papers, but it's not like all of your data is sitting in an archive for the whole world to mine. Astronomy data is all there for everybody, including amateurs. Like, anyone can go download some nice images from Hubble or JWST right now and play with them on their computer.
And so do you talk to other astronomers if your research is sort of the same, so that you're not asking for the same area of space? So, if a colleague in Germany is doing that, like, you ask for that, and then I'll ask for this, and then hopefully one of us will get something.
Oh, yeah. Absolutely. So astronomy is super international, and we do a lot of collaborating to maximize the amount of data we get. So given that it all becomes public, it's in your best interest to, maybe you propose for the infrared and your friend proposes for the radio and somebody else proposes for the visible, and then you all share it among your research groups. But there also is software that checks that you're not observing the same target that has been observed before, because then the time allocation committee won't give you the time. They'll say, go to the archive. It's already there.
Yeah. So a question, could you explain how the JWST could play a role in putting the dark matter and primordial black hole seeds into an experiment?
I don't think I can. Can you repeat the question?
So could you explain how JWST could play a role in putting the dark matter and primordial black hole seeds into an experiment?
So two big science questions there. One has to do with dark matter, which is not what you're seeing in these images. You're seeing the visible matter. JWST will be very powerful for figuring out how much dark matter is in galaxies. Primordial black holes is quite a different thing, which is something that comes out of the Big Bang. Now, it is possible, we don't know if primordial black holes exist. If they do, and there's a prediction from Stephen Hawking and others that these objects would, over time, actually evaporate. And at the last moment of their life, they would give out a burst of emission. It's not impossible, if that theory is correct, that JWST could see that. So I think JWST could potentially intersect with that field of primordial black holes. The black hole experiment side, though, I would say all of astrophysics, what we can do is measure on big scales in the universe, is there dark matter? How much is there? Where is it? And a few properties of it. And then experimental physics has to try to find it in the lab and measure it. And so I think there's always a nice synergy between what the astronomers are doing, figuring out, is there dark matter? Where is it? How much is there? And that can feed into the particle physicists who are doing experiments in the lab. So I'm not sure if that answered it, but JWST will certainly be useful for mapping out dark matter in galaxies and may or may not detect primordial black holes. We don't know that they exist. So.
Great. Well, thank you. Hopefully that helped. I think it was Maddie that asked that. Okay, so let's get to some lensing. In one of your pictures, you showed the lensing effect in the JWST picture of the galaxy cluster. Is it possible we're seeing some galaxies projected on both sides of the cluster, and how would we know?
Yes, we are. So there are definitely galaxies showing up in two places on this image, which is mind-blowing. So if you talk to Isaac Newton right now, he would say that can't happen. Light doesn't feel gravity. Light doesn't have mass. That doesn't make any sense. But with Einstein's theory, lensing, light can actually, from the same object, so everything is giving off light in all directions, multiple beams of light from the same object could go out into space, be bent, and end up in your telescope. And what that would look like is the same object on the sky in multiple places. And this is not new to this image. So the Hubble Space Telescope sees this all the time. And we also can see this effect from ground-based observations. And so the way to figure out you're seeing the same object, to really convince yourself that it's the same, so you can visually inspect it and it can look similar, but you can take a spectrum. The spectrum should be identical, and that happens. So we do that. We find these arcs on opposite sides that are the same galaxy viewed multiple times, go with a more precise instrument, do a spectrum, and you'll find it is the same object with identical chemistry.
And that's what the Canadian contribution has helped with? Is that what the, no?
So the Canadian contribution nearest could help if those lenses are bright enough, then you could get a spectrum simultaneously of both. That's possible. Hasn't been used for that yet that I know of, but it could be. But it could be,
okay. Okay, so some questions about redshifting. So would redshifting of light cause issues with spectroscopy, decoding exoplanets, atmospheres, or compositions of a galaxy?
So the redshifting effect is really important for distant galaxies. The further away an object is, the bigger this redshift. That's called cosmological redshift. And the effect it has on the spectrum is that all of the spectral lines are shifted. The good thing is they're all shifted by exactly the same amount. So let's imagine I have a hydrogen and oxygen and a neon line in a spectrum. If that galaxy is far away, they're all going to be shifted by a certain amount. If that galaxy is further away, they're all going to be shifted equally further away. So we can still understand the fingerprint of the different elements, even though they're redshifted. But you also asked about the extrasolar planet. And so anything within our own galaxy does not have this cosmological redshift effect. But there's another kind of redshift, which is due to motion. And so that is the Doppler effect many of you may be familiar with. When an ambulance comes towards you, it sounds different than when it's going away from you. And the same thing to some extent happens with light of objects moving towards you and away from you. So if it's moving towards you, the light waves pile up and the object will look a little bit bluer, and moving away from you a little bit redder. And so for a planet orbiting around a star, it has all of its spectral lines will have little tiny shifts as it orbits around the star. And that's something that we can measure. And so that effect is something that's certainly understood. But if you take a quick spectrum, then you can kind of do it in a fixed frame and not worry about it so much.
I remember the Doppler effect, yes, from class. Okay, so a few more questions and I think we'll wrap up because we're already over 1:30. So thank you everyone for staying with us. So a couple people have asked the same questions, like what's after JWST? So let's say we get 20 years. Are they already starting to think of what they want to replace?
Yeah.
And what will it look like? What would the technology be like?
Yeah, so definitely everyone's always thinking ahead to the next thing, and particularly because the thinking on this telescope started in 1995, 1996. So it's been a long time in the making. Space is really hard and expensive, and especially a telescope that you can't fix. So when we build a telescope on Earth and instruments on Earth, if the computer board doesn't work, swap it out. If some of the electronics are not perfectly soldered, no big deal. You have an engineer who fixes it, you have a technician who takes care of it, it's all good. You can't do that with space-based things. So these teams have to build perfect instruments that can survive vibrations and can survive space, you have to plan way, way, way in advance, and it's really hard. So already the next generation things are being planned, and the one that most naturally follows from Hubble and JWST is a proposal that's already pretty far along in development, although not yet fully funded, for a telescope called LUVOIR. And LUVOIR will simultaneously do ultraviolet, optical, and infrared. So instead of having different telescopes for these different wavelengths, it will have different detectors that are optimized for these different wavelengths. So the power of that is there's a lot of interesting astrophysical phenomenon that you want to see not just at one wavelength or not even one part of the wavelength spectrum of the spectrum. You want to see everything to see all the physics of what's happening. And so really ambitious proposal for a telescope way bigger. I can't remember the final design, but 15 meters or something, way bigger than JWST, and simultaneous UV, optical, and infrared.
And where because going back to your discussion on, there's sort of an optimal place to put a telescope. So would it be in sort of close to the JWST?
Yeah, so the good thing is that L2 point is not like a pinpoint. So that's a big area of space. And actually JWST is not the first and only telescope to be launched there. So we have other missions that have also gone there, not to do this kind of imaging, but to do other kinds of infrared science with lower resolution. So that's a popular place to launch things. And I think that's where the next generation of telescopes will go as well, will be to that nice Lagrange point, which is quite stable. It doesn't take very much fuel, close enough to easily send signals to the Earth, and far enough from the Earth to not feel the infrared emission of the planet.
Perfect. Okay, well, let's close up with this last question from Karen. What are you most excited for with respect to images and data from JWST over the next few years?
Oh, it's really hard. So I'm torn between two things. One thing is the detail in galaxies that you see with this. So the kind of amazing, I study galaxy evolution, and to be able to see the gas and the dust with this kind of spatial resolution is phenomenal. So probably in my research group, it's data like this that's going to be the most interesting. But I started out my research studying the more distant universe, doing cosmology, and seeing that deep field image and just imagining someone at some point in one of those images is going to find the most distant galaxy ever seen, maybe one of the first galaxies that ever formed after the Big Bang. And that is also incredibly exciting. So those are the two things. So detailed studies of closer galaxies where we have the resolution to do stuff we couldn't do before, and the very first galaxies. But that's because I'm a galaxy person. My friend across the hall doesn't care about any of that. He just wants to see those planet atmospheres. Give me more planet atmospheres. So it depends on your science interest.
Of course, yes, like everything in life. Well, Laura, thank you so much, Dr. Parker, for taking time out of your busy schedule to give us this presentation. Lots of posts saying thank you. Your enthusiasm was definitely, detected, and people really appreciated that. And as a student of yours, I really appreciated your ability to make it very layperson friendly. So thank you. And thanks, everyone. Thanks, everyone, for joining us. We'll send a copy of this hopefully by the end of the week or early next week, so you can watch that and share it with your friends. Thanks again, and we look forward to seeing you at another online event. Bye now.